let's talk about this limit first, and then we'll go to any other question you may have. There are certain graphs, certain functions that we have to have in the back of our minds at all times. We're given a limit. Obviously, I have to plug it in. Although, if you remember, there is some sort of a contradiction, but you know what I mean. We have to plug it in to see what it is. So when I plug in 0 in this function, my memory has to come up with this immediately. Because if I don't come up with this and I don't know how to graph 1 over x, I may have difficulties in finding the answer. Was it 0 from either side? Was it 0 from the left? Or was it 0 from the right?
It was the left, right, and both.
Okay, so let's start with the left first. So then we will look at the right. And then both, okay? Is that what you meant?
Yeah.
Okay, perfect. Okay, so let's take a look at the first one. 0 from the left. What does that mean, 0 from the left? Look at the graph and tell me, where does 1 over x go? That's my first thought. It has to be my first thought. Where does this go when x approaches 0 from the left? Good, perfect. How much is negative infinity plus 1?
Still negative infinity.
Of course. How much is 7 divided by infinity? Let's talk about that. So, yes, of course. Of course. Divide $7 by 1 billion people. How much when you get to me, how much will I get?
Nothing, basically.
Of course, you're gonna run out of money in 7 people or 10 people. Good. So if that approaches 0, then the limit is 0. Okay, let's look at 0 from the right. Where does this go? Notice one thing. How come that I didn't start somewhere else? I have to start with the inner function. I have to evaluate the inner function first and then go step by step to the outer function. Okay? When we're going to differentiate these functions, we're going to start from the outer and go to the inner. But when we evaluate any function, we have to go from the inner function to the outer function. So the first thought is I have to evaluate 1 over x. So where does 1 over x go? Look at the graph. When x approaches 0 from the right. How much is e to infinity? Oh, okay, so let's go back here. Sorry. Okay, so e to negative infinity, I talk too much instead of paying attention, is e to infinity. Careful. Sorry about that. My mistake. So when x approaches 0 from the left, 1 over x approaches negative infinity. And e to negative infinity is 1 over e to infinity. Where does this go? Of course, it's 1 divided by billions. Of course it's 0. So how much is 0 plus 1? How much is 7 over 1?
7.
Good.
That lines up with the answer.
Okay, now that's a different story now. E to infinity is infinity, and that's what it was. 1 plus infinity is infinity. 7 over infinity, that is 0. That is no discussion there. Okay, so then what do you conclude about 0 from either side?
Doesn't exist.
Perfect. That's the reason why we have to look at the graph before we analyze this function. Because from the left approaches negative infinity, but e to negative infinity approaches 0. But from the right it approaches infinity, but e to infinity is infinity, where infinity plus 1 is infinity. 7 over infinity would be 0. And therefore, the limit from either side does not exist. Very good problem. Anything else? Yes?
Wait, could you explain what for the one coming from the right, why is that 0 again?
Here?
Yeah.
Because this is infinity. How much is infinity plus 1?
Oh, so that takes away the e.
e to infinity approaches infinity. This piece
Oh, 1 over, okay,
approaches infinity.
I got you.
Infinity plus 1 is infinity, and as we discussed, 7 over infinity approaches 0.
Okay, that makes sense.
Yes, please, Sabrina?
Why the one coming from either side wouldn't exist?
The limits have to be the same. If they're not the same, the limit doesn't exist. If from the left is
Oh.
7 and from the right is infinity, from the left is 7, from the right is 0, the limit from either side cannot exist. Good. Other questions for me?
Okay, it was number 11.
Okay, number 11, we found it.
Sorry.
That's fine.
There it is.
Um,
Cosines and all. Not good with these.
you want me to read?
Yes.
So,
Yes, we did this problem in class with a different function, identical situation. That's why I did it. So this is the function, right? And we're asked to estimate the value of the limit of f of x when x approaches 0. Right? So limit of f of x when x approaches 0. Okay. So all you have to do at this point is exactly what we did last time, but not even using the difference quotient or the slope of a secant line. There's no need. So you are asked to evaluate this function. If you plug in 0, you're not going to get anything because it's 1 minus 1 over 0, right? But there is hope, right? So when you write limit as x approaches 0 from cosine twice x minus cosine x over x squared, you know it's 0 over 0. So it's worth investigating, for sure. In a later chapter, we will learn how to deal with this without plugging in numbers. Okay, but right now we don't have the tools. So let's go and put in the function. It's way simpler than you think. So let's put the function in y equals. Make sure that the mode is in radian mode. In y equals. Make sure you put parentheses around the numerator. So cosine twice x. Please put parentheses around 2x unless your calculator is way more sophisticated. And then divide by. There is no need to put x squared in parentheses, but I do. Okay, so now we go to second and table set. I always have to redo this because there is a deep freeze here and it raises everything I do the moment I log out. So now we go to table and we want to go to the left and from the left and from the right of 0. So I'm going to start with something big, 0.2, and then 0.1, and then 0.01. And then 0.00000, I got tired of it, just give me the answer. So I got the answer. Ah, you're too patient. Sorry about that. Okay, so I put the function in, let me show you, I'm sorry. I thought I already turned it on. Okay, so I have the function, I have parentheses around the numerator, I also have parentheses around the denominator. Since there is only one term, there is no need, but I like to put parentheses. So then you go to second and table. You plug in numbers close to 0, as close as you can, because if you put 0, you're going to get an error. So that was from the left, and now let's put in from the right. I mean, this is clear. So then 0.1. Yeah, I wanted to put the negative. So yeah. Okay, so negative 0.2, negative 0.1, and negative 0.01, and negative 0.000001. I didn't think that this could ever create an issue. You didn't even have to create a function or anything. You were just asked to find the limit from the left and right. So what is the limit then?
1.5. Negative 1.5.
Negative 1.5. That's it. Later on, as I said, we will determine this limit without the calculator. So what was the difficulty here? So I understand.
Well, I was getting exactly what you just got, but I read a sign was saying that it wasn't correct. So I don't know,
Maybe you forgot to put parentheses or something.
yeah, I don't, it was probably a technical issue, but it
That
was
is also-
driving me crazy.
That is also possible, so be prepared for that. Yes, very good. Anything else? Anything else you worked on?
I have one, give me a second.
Yes,
Let's get to
please.
it.
Yes,
It says, it's number 5 and 2.2. It's the last one that we don't have an equation to look at. And it asked me to find the instantaneous velocity, or the estimated or guessed or something like
good,
that.
good.
And I kept getting it wrong.
Okay,
My
do we have a
connection-
graph or we have to be
Yeah.
given something?
Number 5.
They give you a table, and then I have a bunch of answers, but I don't have.
Very good.
No, the 2.2.
It might just be different. Oh, wait, 2.1.
I wish I could, for whatever reason, my phone does that.
I can look here, may I?
Look, right it is.
That's 2.1.
My connection isn't, that's not the right one. My connection isn't lined up right now.
So we're looking for number 5.
Number 5. So I'm not sure which one I'm in there. Yeah.
So this is number 5. Is this the one?
No, not this one. My connection would allow me to change the sound.
Is it in 2.1?
I believe so. Yes, it is, because that was the one where you get like a few buttons. Yeah, bingo, got it. He got it. So, how did you come up with this number? Because I thought I came up with something similar, and they kept telling me no. And then it became a game where I just started guessing a bunch of numbers, trying to get, it kept changing my equation. I was like, at this point, I just guess.
Okay.
So the last question there,
This one?
yeah.
Okay. So in this problem, we are given not the function. We're not given the graph. We're given some values. I think, so the values in red, did you put them in or?
Those were just like, everyone's, I'm pretty sure, changed.
We all got different ones, and the one I ended up with, they aren't too far off. I ended up with
Okay.
1.2, 5.2.
So
and
it doesn't matter. So it's f of 3, which is 10.5, minus f of 1, which is 1.1, divided by, of course, 3 minus 1.
So you should have S of B minus S
I
of
see
A.
how you got the first four, because I got the,
Okay.
when I got.
Estimate the instantaneous velocity when t equals 3, right?
So you look at the 3,
Yeah.
but then you want to take the A's and B's of the right side and the left side, so the 4 and the 2, and then you subtract them. Or you pretty
You
much plug
can,
them in.
what you could also do, if they are equidistant, at the same distance left and right of 3, 2 and 4, right? I am 3, 2 and 4 are at the same distance away from 3, correct? You can just average them.
Yeah.
It doesn't always work for all functions, okay? Doesn't, it depends on the function. But in this particular case, it works. So you will average, so since we are looking at 3, you will average the 3 and 2, this one, with the 3 and 5, this one, add them up and divide by 2.
So I guess I did, I plugged in the 4's value and then the 2's value, and then subtracted the 4 minus, I guess it's the same answer.
Yeah, okay.
So you could do this, but again,
Just be careful.
caution, yeah. Very good. Anything else for me? Yes,
It was. It was number 15.
15.
I don't think it was anything crazy, but it was just another one about the exponents as a fraction.
Estimate the value of the limit as x approaches 0, 1 plus x, everything raised to 1 over x. I can't give you directly the answer to this.
Well,
We
just
will-
like how to kind of.
Yeah, of course I will. But I can't give you directly the answer. I think it's a little blurry, isn't it? Okay. Because we are going to discuss this in detail, there are two limits that are paired together. So we're going to discuss this in great detail later on, not in this chapter. But let's talk about it. So let's put it in. Here it is in y equals. So let's go to y equals and clear, and let's put the function in parentheses 1 plus x. Close the parenthesis, caret, do not forget to put the power in parentheses, otherwise you're not going to get anything. So it's 1 over x raised to power 1 over x. And now we go back to second and table. And we're going to go from left and right as close as possible, since I already have those numbers plugged in. Here's what we get. So from the right-hand side of 0, we get closer and closer and closer and closer to 2.7. From the left-hand side of 0, we get closer and closer to 2.7. Is there something that we know about this 2.71883?
It's E.
Excellent.
Oh.
Yes,
Put that
but
together.
we are going to discuss this. We're not going to determine the limit like this anymore very soon, right? So the answer is E. Correct. Very good. Thank you for bringing that up. It's good to see it ahead of time, and then we're going to determine the exact, and you'll see why and how, et cetera, et cetera. Anything else? Okay, so I'd like us to work on this for a few minutes. Let's talk about it. This is really the most important topic so far. So let's work on it. Open notes, open book, but not your computers though. I hope not to spend more than 5 minutes on this, hopefully. Wait 2 more minutes, okay? Dante is here, Hannah is here, Thane is here, Paige, yes. Vicky's here, Tara is here, Alex is not, right? Yeah, Alex is not. Mason is here, Reese is here, Mari is here, Brady is here, Colby, Sabrina, and David, thank you. Okay, are we finished with this? Almost, okay. How are we doing? How are we doing?
Don't look at that, sure.
How are we doing? Okay. One comment first. Please do not multiply the factors in the denominator. Please do not multiply the factors in the denominator. Please do not multiply the factors in the denominator. We want them factored. We work hard to factor them. We want them factored. And you will see many times this semester why. Don't waste your time on multiplying the denominator. The factors in the denominator expand the denominator. Okay, bottom line, too few to mention. I don't like what I see, so let's do this together. But you're gonna get the same one or a different problem for a different problem next time. And next time, and next time, until this is done correctly. Okay, so I see, and allow me to say, not everyone watched the videos. We had an example on the assessment, on the skills assessment. It was not a rational function, it was a quadratic function. So let's start from scratch, okay? I expect everyone to do the work, everyone to watch the video or other videos and do the problems that we do in class, whatever works for you. But I don't want to see this situation again, please. Is that okay? Perfect. So let's take a look at the function. The function is 5x plus 1 divided by 4x plus 2. And of course, x does not equal negative 2 makes sense because I have to write a condition that so that this function is defined all the time. It is defined everywhere except at negative 1/2. Okay, so now I remember that the difference quotient is f of x plus h minus f of x divided by h. And as we discussed last time, sometime last week, this is clear. This is clear. There is nothing I can do to it, but I have to work on this piece before I put those three pieces together. Also, I remember that two things have to happen every time I calculate the difference quotient for any function. What are those two things in the correct and appropriate order? What is the first thing that has to happen?
Anything that doesn't have an H should cancel out.
Absolutely. Otherwise, I know I have to go back from scratch. Something is wrong. Excellent. The second, somehow, I don't know how, it has to be legitimate, of course. I'm not going to erase it, but it has to go away. Excellent. So let's first identify this f of x plus h. Can anyone dictate f of x plus h? Good, so then 5x plus 5h plus 1, and the denominator, 4x plus 4h plus 2. Everyone in agreement with this step? Everyone? Excellent, perfect. So now I'm ready to put pieces, all these three pieces together. So I'm gonna say the difference quotient. So in this class, in the previous class in pre-calculus, I gave my students the definition. But moving forward in this class, we can't. We have to remember the definition of the difference quotient, or the formula if you want to call it. So obviously I'm going to copy this instead of this, and I get 5x plus 5h. You can take that, please. That's fine. Minus 5x plus 1 divided by 4x plus 2, everything over h. Is this clear? Is this step clear? Understood, everyone? I didn't do anything, I just put them together, right? I haven't performed any operations yet. Good. Here's our next step. To find the least common denominator. So obviously this is a fraction because it's h over 1. And the numerator has an LCD. What is the LCD of this subtraction? The least common denominator would be
4x. Wait.
4x plus 4h plus 2 minus 4x plus 2.
multiplied by 4x. Okay, so we need to talk about that, so I'll come back. So when I add or subtract fractions, I find the least common denominator to be 6 because these two are prime numbers. They have nothing in common. They're not factorable. So then the product has to be the least common denominator. 2 is multiplied by 3. Therefore, the numerator has to be multiplied by 3. 3 was multiplied by 2. So therefore, the numerator has to be multiplied by 2. So then 3 times 1 plus 2 times 1, which is 2. So that's how I get 5/6. If I have minus here, the procedure is the same. It's just that I have minus here. I know that this does not look anywhere near this, but that's what it is. It's nothing else but subtraction of two fractions. So therefore, this is a factor. You can say, oh, I can pull out the 2. Yes, that's true. But still, these two have nothing in common other than that number 2. So the least common denominator must be the product of these two. So it must be 4x plus 2 and 4x plus 4h plus 2. Remember, please, when we find the least common denominator, we cannot add or subtract the denominators. It's only a product or finding the LCD. Is that clear, everyone? Agreed? Okay, perfect. So now, like I did here, I asked myself, I multiplied 2 by what, and I got 3, so the numerator gets a 3. 3 by what, so the numerator gets a 2. This is the identical procedure. See, this denominator has 4x plus 4h plus 2, which means it was multiplied by 4x plus 2. So then the numerator has to be multiplied by 4x plus 2. This denominator was multiplied by 4x plus 4h plus 2. So then the numerator has to be multiplied by the same thing, 4x plus 4h plus 2. So please remember, you cannot drop any of these denominators. They do not go away. They will not simplify with anything. Okay? Only two things have to happen. At the top, but we haven't finished the top. We haven't even written the top yet. At the top, all terms without h must go away. It's a bonus that some terms with h will go away, but that's fine. I have no control over that. But all terms without h, mandatory, have to go away. And then at the end, the h, that h over 1 from the denominator has to go away. Okay. So, careful how we multiply. The reason why I don't write them in parentheses side by side is because some of you will be tempted to simplify in a sum, and I have to avoid that. Will you be allowed to use a different method? Yes, gladly. If you have a different method that works for you, do not change anything. Okay, so 4x has to be distributed to these three, and then 2 has to be distributed to these three terms. 4x times 5x.
20x.
Right, watch me run out of time, paper, or, yes, I will write up here in a minute. So just watch me, I always do that. So this time I'm warning you. 4x times 5h, 20xh, excellent, and plus 4x plus times 1, which is 4x. I'm done with distributing 4x to these three terms. Now I distribute 2. So then plus 10x plus 10h and plus 2. And as promised, I will run out of room in a blink. Okay, and then now you have to be very careful. Always, I shouldn't say always, I recommend starting with the binomial. Instead of distributing, I would do 5x to these three and then 1 to these three, but all terms, everything will get a minus. Everything will be changed into a negative sign, a negative term. So negative 20x squared and negative 20xh and negative 10x and negative 4x and negative 4h and minus 2. In case you're trying to ask or wonder why it's minus minus, no, it's not the double minus. I'm just saying that it hasn't ended. It hasn't ended. It's continuing. Yeah. Now let's look at the numerator. And here's what I see. I see a 20x squared with a negative 20x squared. I see even a negative 20xh with a positive 20xh. That's a bonus, which is good. A negative 4x with a positive 4x. The negative 10x with a positive 10x. Positive 2 with a negative 2. And I see only 2 terms left at the top. And those 2 terms left at the top are, right, so I'm going to circle this and continue here. So the numerator now, look what I'm doing. The fraction line is right in the middle of the equal symbol. The numerator has 6h. The denominator has to be copied, mandatory. It cannot go away, and you cannot multiply it. And now I multiply by 1 over h. Only now I'm in stage 2 or step 2 or whatever you want to say it, or call this step. And this is final. So the difference quotient for this function is 6 over 4x plus 2 over 4x times 4x plus 4h plus 2. And no one can change that. Again, the denominators do not need to be multiplied. The factor in the denominator would never expand the denominators ever, ever, ever. And the product of the 2 factors in the denominator cannot go away. Yes?
So you can't factor out that 2 and then.
You can.
And so.
Yes, of course. Yes. Yes. That's a very good suggestion. Yes, you can factor out from both, actually, and get a 4. And this is 2x plus 1. And this is 2x plus 2h plus 1. And you will simplify it 2. And the final simplified form is that.
Wait, when you take out the 2 instead of the 4?
The 4, there's a 2 in here from here and a 2 from here. And it's a 4.
Wait.
Oh.
4x plus 2 has a factor of 2 that I pull out. 4x plus 4h plus 2 has another factor of 2. And when I multiply 2 by 2, I get a 4.
Oh.
So 2x plus 1, and 2x plus 2h plus 1. And this is final. Any questions? Okay, I'd like to continue to 2.3, in which we learn limit laws. So we're going to talk about limit laws. Any questions here? Is this okay, everyone? Yes? Feeling better about this one?
Yeah.
Okay, it's not an easy situation. I have to agree with you, or just be honest and tell you, a complex rational expression is not an easy situation to work with. So, okay, and you'll see what happens next with that difference quotient. But for now, we're going to look at 2.3 limit laws. There are about 11 limit laws that I will list for you and we will discuss. But the most important part of all this is the conditions. The conditions are extremely important. What are the conditions? We have to assume, and if that doesn't happen, the limit laws are not applicable. We have to assume that the limit of a function f as x approaches a from either side exists. It doesn't matter what you want to call it. Let's call it L. It doesn't matter. It's a number. When we say the limit exists from either side, we really mean that it's a number, not infinity. And let's also assume that limit as x approaches a from g of x is another number. So this one exists as well. So let's say this is m. Based on this assumption, and if this assumption is not validated, the limit laws fail. So here is the first limit law. Limit as x approaches a from a sum of these two functions. If and only if the limits exist, like we assumed here, you can use any letters. I just used L and M because that's what the book uses, but you can use A and B, it doesn't matter, any number. Then you can split the sum into two limits. And yes, if the first one is indeed L, the other one will be, assuming it's indeed M, then the limit is L plus M. So in short, well, how do we remember this property? The limit of a sum is the sum of the limits. Okay, I like to put two laws in the same. I'm not lazy, I can write it again, but we should remember them together. So the sum or the difference of, so the limit of a sum or a difference of functions, if conditions are fulfilled, both limits exist, in other words, then we get either the sum or the difference of limits. Any questions so far? Okay, number 2. So this is 1 and 2 if you want. Number 3. Limit of a function of a number times a function as x approaches a from either side. So c is a constant. To be assumed not 0, because if it's 0, then the limit of 0 is 0. So we assume it's not 0. In that situation, we are allowed only if it's a factor, right? In this case. So we are allowed to move the number in front and write limit of f of x as x approaches a from either side. This will be c times L. How come? Because we assume that the limit of f of x exists from either side of a, and that is L. Questions so far? Number 4. The limit of f of x multiplied by g of x as x approaches a from either side. What do you think this will equal to? Common sense. Right, the product of limits. So this will be limit as x approaches a from f of x, of course, multiplied by the limit of g of x as x approaches a from either side. And in our context, we are going to say that this limit equals what?
L times M.
That's it. In other words, the number that is the first limit times the number that is the second limit. Any questions so far? Okay, number 5. So how will you remember this, for example? The limit of a product is the product of the limits, exactly. Perfect. Assuming conditions are fulfilled, otherwise the limit law cannot be applied. So let's say x approaches a from f of x divided by g of x. Common sense, what do you think this will equal to? Yes. So the limit of f of x as x approaches a over the limit of g of x as x approaches a. And before I write the answer, I have to write a big if. What is the big if?
G of x not equal to 0.
Yeah, we can say the limit, but you're right. And that means that also m does not equal 0, right? So then we say it is L divided by m only under the condition that the denominator is not 0. Any questions so far? I want to give a short example and then we move on to the rest. So let's say I have a limit of 1 over x plus 2x when x approaches 0. And I just studied that the limit of a sum is the sum of the limits. And I write this. You agree, you disagree? Is it acceptable?
Yeah.
Anybody else?
Can't you not have 0 in the denominator?
So of course that limit does not exist. No. This one is not a number. This one is a number, but this one is not a number, so I can never do that. Not with these two functions. With other functions, yes. But not with the limit of 1 over x as x approaches 0 from either side. I know you're going to get sick of these functions. I'm going to graph them and graph them and graph them. Sorry about that. So what do you say about the limit from 1 over x as x approaches 0 from either side? dne. So this is dne indeed. So we cannot use the limit law. We may be able to do something else, which I'll show you later, but not use the limit law. Excellent. Moving on. Questions? Remember the conditions. Okay, next step. Limit, number 6. Limit of f of x. And when f of x is raised to a power, as x approaches a from either side. And let's assume that n is a positive integer. Because if it's negative, this story is different. It's limit of 1 over something, right? So let's assume for now that this is a positive integer. So, and this is something that is an extremely important property that we are going to use a lot in the first 2 chapters, especially in the second chapter, the third chapter of the second chapter of the course, but the third chapter in your book. Okay, let me explain something here. This notation is an operator. This notation is an operator. This notation is an operator. Of course, they're different. The first one is a function that I don't know. The second one is natural log, which is an operator or a function. The third one is a square root function, which is also an operator. But so is this. This is also an operator. It's an operation. Square root is an operation. Natural log does something. Limit does something. They're all operators. Okay, so here This is what happens, and this is your first exposure to such a theorem, in which I can swap the operators. I have one operator outside, one operator inside, and I'm allowed to do this under certain conditions that I will explain in 2.5. Just remember, we're not allowed to do that all the time. But under certain conditions, I'm allowed to. And this is what I'm going to do. I'm going to move the limit operator inside and put the power outside. Extremely important property. And I'm going to write the condition so it's there for us. So it's this. Limit of f of x as x approaches a. And of course, the answer will be L raised to the nth power under conditions in which we denoted the limit by L. So this happens under conditions of continuity. I want the condition to be there, but I can't explain it just yet. We will talk about it in detail in 2.5. So we are allowed to swap operators, and we will in many occasions, as I said, only under conditions of continuity. And I'll explain the theorem later. In this case, we get L to the nth power. Okay, the next one, number 7. And then we're going to apply them in problems. So, of course, the next one is, I don't like the order that is presented in the book. I want to keep these two together, which the next one should be limit of the nth root of f of x as x approaches a. Of course, n is a positive integer. Of course, if n is even, then the quantity under the root has to be positive. But for now, let's say this. You understand that this is the same situation because the nth root is still a power. What power is the nth root? Which other way I can present the nth root of f to the x, f of x?
Wouldn't it be 1 over n?
So it's the same thing, right? What's the difference between these two? No difference, still a power. So we're going to apply the same procedure, swapping of the operators, the operator nth root and the operator limit. So the nth root comes outside as an operator, and the limit goes inside. Limit of f of x as x approaches a. And of course, this will be the nth root of a, of L. So that's why I wanted those together. So you remember them together. Power n or power 1 over n, the same procedure. So let's look at 8. The limit of a constant as x approaches a. What do you think this will be?
Constant.
Of course. Who cares where x is going? The constant will never change. Number 9. It's the limit of they jump to x to the n power. No, I want to discuss limit of x first. And then in the same limit, we can discuss x to the n or the nth root of x and so on and so forth, which are all the same with the function. So I don't think that these should be addressed separately, but that's okay. So what do you think?
A.
Very good. Under the same, let's write the limit of x to the n as x approaches a. It's the same rule. The power is an operator, so this is limit of x, everything raised to the nth power. I'm swapping the operators under conditions of continuity, and I get the same thing. What do I get? If this is inside is a, what is the answer? Right. And the same thing with limit as x approaches a from the nth root of x. I swap the operators again. I have the nth root of limit as x approaches a from x. So I know it's the nth root of a. Not a big deal. I think that these should be under the same. Of course, n is a positive integer and the conditions have to be fulfilled, so. And positive integer. That's basically it. So if you want to call this one 10, and if you want to call this 11, that's it. I would like us to use these. Let me see where I'm with my video. Okay, I have to